I'm Nick Adams, as JM introduced earlier, and I wanted to talk to you all about what's going on with NVMe 1.4, the base spec that got released this last couple months. And so we're going to go through that. We'll start here. So one of the things that Peter talked about earlier was I/O determinism, and how we're looking at NVMe working for some of the hyperscalers. One of the things that I/O determinism is intended to do is to really focus on tail latencies and being able to give a deterministic response time for the OSs that are using it. So one of the things that this is looking at is basically separating out the drive so that the sets that are being used don't interact with each other. One of the things that happens with NVMe drives is that the background tasks, if you're sending things, multiple commands to the drive across it, they'll interact with each other. So each of the applications will use reads and writes that will then impact other applications that are using the reads and writes. So what we've done here is we've actually separated out the drive into multiple what we're calling NVM sets. And so with that, we have provided the ability to understand exactly how long those latencies are going to be. So as the drive is going through and doing basically lots of different reads and writes, on the left side, we end up with interaction between those different processes. And we need to make sure that that isn't the case. So what we do is we split up the drive into multiple sets. We provide a mechanism for the operating system to be able to do this in a way where those read and write operations don't interact with each other. And it provides the ability for the OS to know exactly how long that is going to take during a particular deterministic window. And outside of that window of time, then we allow the drive to do background tasks that would do those interactions. And so what that does is during certain windows of time, the OS is able to know exactly how long the latencies are going to be. And in those other periods of time, then it allows the drive to carry on those background tasks. And because of that, then you're able to get these deterministic latencies. And so that kind of is shown here on the right, where we've got the drive split into multiple different sets. And as you interact with each of those sets during different points in time, you're able to get deterministic latencies. So that would be I/O determinism. With regard to interface optimizations, what's going on here is we've provided a bunch of different mechanisms for the operating system to better interact with SSDs. We've got I/O and performance endurance hits. So what this is it basically says, hey, here's the optimal size to be able to do read and write operations with a particular namespace. This allows for optimal kind of performance from an OS perspective. We have endurance groups. These were added to NVMe 1.4, and what endurance groups do is they basically make it so that across a particular portion of the drive, the endurance for that particular namespace or set of namespaces is kind of managed together so that the wear happens kind of equally over that set or that group of sets. This allows so that we don't have kind of mixing. You're able to kind of manage the endurance of particular sections separately from other sections, and the OS is able to control this directly as opposed to it being only managed by the drive. We provided namespace granularity. That allows for the namespace size and capacity to be able to be managed by the OS. We have submission queue association. So this feature, what it does is it allows the host to associate a particular submission queue with a particular NVM set. And so this provides just kind of the ability to allow certain kind of bandwidth to a particular set and kind of manage that across sets. The other one is a verify command, and what this does is it allows a drive to be able to say, yes, the data can be read, but it doesn't have to send all that data across the interface. So what we've got here is basically multiple ways for a host OS to be able to kind of more closely and kind of more just optimized way of being able to interface with SSDs. Another feature that was added to 1.4 is the persistent memory regions. So what this is it's basically an area of inside a PCI space where the drive is persistently keeping that data, but it's a memory region. It can be used for storing command data. The contents in this section or in this space, they persist across power cycles, resets, and the disabling of the region. So it's a persistent area that we can use for storing data, but it's memory addressable. And so what this can be used for is things like logs for RAID or erasure coding or databases, journaling or metadata. So there's many things where it might be useful to have this kind of memory interface for being able to persist data, and that's the idea behind what we're providing with the persistent memory regions. Another one that Peter alluded to earlier was the enhanced telemetry capabilities, basically persistent event log. And the nice thing about this feature is that it basically builds up a scaffolding or kind of an infrastructure that can be used both by SSD vendors as well as by customers of those SSD vendors. The idea here is that you're able to use a standardized interface for collecting information that's necessary for debugging your kind of enterprise infrastructure or your hyperscaled infrastructure. You know, this can provide things like health snapshots or information about firmware commits. It's able to, talk about when formats start or complete, and basically any information that a drive manufacturer needs to be able to collect to be able to do debug at scale, they can do and collect that in a persistent way. And the OSs, the host, can actually use a common mechanism to be able to save off that information so that an SSD vendor can actually debug those things that are done at scale that they may not be able to do on their own. So, one of the nice things here is that it provides infrastructure that's useful both from a deployment standpoint as well as infrastructure that is useful from an SSD vendor standpoint. Another functionality that is new in NVMe 1.4 is the administrative controller. And the administrative controller is a new type of controller. That new type of controller is specifically useful for enclosure management. One of the things that's really nice about this particular functionality is that it requires minimal functionality. You don't have to implement all of the I/O queue. Well, you don't have to implement I/O queues at all in this particular controller. It's really about implementing the admin queues. And the idea here is that it allows for supporting NVMe in-band without having to do all of the I/O infrastructure. Also, another key feature of the administrative controller is that it has a different PCI interface. Basically, it has a different type. So you can load a different driver against an administrative controller than you would load against a standard NVMe drive. And so this allows for some kind of customization of that particular interface. I think that's kind of the key thing here, is that we're really working to enable the enclosure management with the in-band NVMe MI interface. One of the last things that we want to kind of point out with regard to NVMe 1.4 is that we're really working to mature the specification. As Peter was alluding to, this is starting to be much broader acceptance. There's a lot more use cases that are being taken into account. And so one of the things that's key there is to kind of clean up some of the things that are either inconsistent in the specification or that are unclear in the specification. We need to be able to effectively just mature the spec in a way that allows for a broad adoption and a broad implementation. And so with that, we've added features like Rebuild Assist, which are responsible for kind of improving some of the recovery scenarios. We've got a mechanism to ensure vendor-specific events don't collide. So, effectively, it's called UUIDs for vendor-specific info. But what this allows is, one vendor uses a particular UUID to be able to kind of tag its events, and another vendor will use a different one, and so you don't end up with collisions here. Again, what that allows for is deploying multiple vendor solutions inside of a large, kind of data center without getting collisions on debug, those types of things. Let's see, multi-host shared stream write. I think this one's kind of self-explanatory a bit. Enhanced command retry, so adding robustness under load. And namespace write protect allows a finer granularity control over areas that are write protected, basically for namespaces as opposed to entire drives. There's a couple of dozen areas in the specification that were updated just to provide clarification, to provide, just to get rid of inconsistencies and to make sure that things are very clear so that regardless of the vendor that you're working with, things are consistent. And that's something that's really important as we mature the specification and we broaden our deployments. So the next thing that I want to talk to you guys about is really refactoring of the NVMe specification. So Peter alluded to it. It's something that we're putting a lot of effort into. And one of the keys here is with regard to needing to kind of understand that there are certain pieces of the specification that, like Peter said, are going to kind of cross that chasm of broad adoption. And there probably are other pieces where we're not going to be able to do that. But we don't want to burden that base specification with all of those details. We want to be able to have a core set of functionality that is absolutely critical and that must be implemented as part of NVMe. But then there are other pieces where I want to be able to focus on the pieces that I know and that I need for my deployments. And so that is kind of the main goal of the refactoring. So, we started with the NVMe base specification. And then we also have added MI, well, I'm not going to talk to MI on this particular slide, but we added the NVMe over fabrics, and there are multiple transports there. And as we looked at what was going to be added for this upcoming, kind of post 1.4 world, there's a key value in zone namespaces functionality. These are new command sets that will be talked about more this week. And then NVMe over TCP and NVMe over potentially some other technology or different types of command sets may come in the future. And adding all of this together is really something that we wanted to make sure didn't happen because we don't want pieces of the spec to be used and other pieces of the spec not to be used. And so in order to kind of do that, we wanted to reorganize things in a way that made sense, that was able to be kind of keeping those concerns separated. And so, we want to keep to the key concepts of NVMe of being fast, simple, and scalable. And with regard to refactoring, that simple piece is one of the things that really came out. If we add a lot of complexity for functionality that is not key to a particular deployment model or usage model, we wanted to look at ways to be able to avoid that. And one of the things that we're using for that is actually the refactoring. Additionally, we wanted to kind of foster those areas of innovation. We don't want to hold back different use models that people will be wanting to use. We want to encourage those that innovation. But we wanted to do that in a way that isn't detrimental to the rest of the specification. We want the broad deployment that is going on right now to continue, and we don't want to burden the spec with those things that are kind of outside of that. So that is something that we wanted to continue to foster. And so creating an extensible spec is part of that. When we look at how the NVMe spec is organized today with 1.4, you have the management interface, which is on the side and will continue to be going forward. But we have the NVMe base spec. Inside of this, we have things like the queuing model, logs, status codes, features. We've got the NVM command set, which is kind of the block command set that everybody's familiar with, and we also have admin command sets for kind of configuring the device itself. We have all kinds of data structures for identifying namespaces, scatter-gather lists, and then we have the PCIe transport. That's defined right now as part of that base specification. And then, we added NVMe over Fabrics, and right now, that NVMe over Fabrics is a separate specification. It's got a discovery service, which is a different type of controller, basically. We've got the NVMe over Fabrics command set, a different set. Some are the same data structures, and some are different, like capsules. Transport independent definitions for TCP and for RDMA. And those things are very Fabric specific. But in doing this, we've got kind of a mix of architectural elements across these two different specifications. And we want to be able to kind of change that model. And so, with that, we're going to move to this new model. Okay? So this is what you'll see in the next version of the NVMe specification. Is on the roadmap, Peter had showed NVMe 2.0. This is kind of the structure that will be used for that. And so what we have here on the left side, we still have the NVMe management interface. It will continue to be a separate specification. But what we're doing with the base spec is we're actually integrating the NVMe over Fabrics portion into that base specification, because we really want the Fabrics concepts to be core and integral to what is going on with NVMe. We don't want to make a separation based on, is this a PCIe thing or is this an Ethernet type Fabric thing? We really want the core aspects of NVMe to be combined. The queuing models, like the administrative commands, controller definitions, those kinds of things. We want to be integrated and in one single specification. However, command sets and the namespaces that those command sets are associated with, we want to be able to do innovation in that space. Right now, we have the block IO commands and the block IO command set and the kind of the legacy defined namespace. That will continue to be there, but that is going to be its own specification and its own definition. Additionally, we have things that are currently being worked on that you'll hear about this week with regard to key value as another type of command set, and also the zone namespaces as yet another type of command set. Those are things that we want to be able to kind of add some innovation on. And other command sets that might come down the road, we want to be able to actually have specifications for those. And again, someone who's going and implementing a zone namespace SSD may not care about how the specification for like a key value interface works. It may not be something that they find critical for being able to get out what they're trying to do. And so we want to keep that separation so that people can innovate in the space where they're working and where their focus is, and allow kind of some of that work to go on in parallel. But anything that is kind of fundamental and is shared across the different types of command sets, again, it will be pushed back into that base specification so that we have consistency in kind of how to interact with these things across the different command sets. Additionally, we want to look at transports as something that is also able to be innovated on. Right now, we have the PCIe transport, which has been kind of fundamental to the specification up to this point. We're working to kind of pull that out so that it's clearly its own specification and it's looked at as a separate transport in the same way that RDMA and TCP are right now. So the idea being that we are able to keep those transports and kind of that layer of abstraction, again, separate, so that if there are new fabrics at some point in the future that we need to integrate, that we can do that, but we do that in a way that's not going to have large impacts across the broader specification. So, again, the key point of this refactoring is not just that we change the way that our specification looks, but that folks folks that are doing implementations look at this from an architectural perspective as well. We want to convey that these are the areas that we expect kind of change and where we expect things not to change as much. And the software architectures and the hardware architectures that are out there should be looking at this as kind of a sign of how that will look going forward. And you should take those things into account as you are looking to do your software designs and your hardware designs in the future. And so with that, wanted to kind of open up to any questions that you all might have. Yes. I think we've got a microphone.
So what's the status of hot pluggability for NVMe drives? Last year, somebody from actually Peter's former company Microsemi, I think, gave a presentation that I was looking at a couple of weeks ago and says wasn't quite there, and it was a long list of issues. So could you just touch on that? Maybe that's going to be covered in other sections.
I can talk to that one. So PCI Express, I want to distinguish hot plug from hot swap. So hot plug in PCIe lingo means kind of managed hot plug. You press a button, the LED turns on, and then power is turned off to the card, and you can pull it out. That's been in PCI Express for a long time. It ships in major OSs. That works just fine. What's been problematic with PCI Express is kind of, async add and removal, where you just yank a drive and have the system continue. And I think really, yeah, exactly. And I think the problem associated with that was largely due to the fact that, PCI Express was an I/O bus, and cards were expected to be plugged into PCI Express. And although it had error handling mechanisms, it was never really, a lot of people didn't implement all the features necessary to handle it robustly. So OSs would lose screen and other bad things would happen. We've been working on this problem for 10 years, chipping away at it slowly. I think that a lot of good work's been done by a number of different vendors. You mentioned Microsemi. But also what's been done is there's a new ECR that's been done in the PCI SIG to kind of specify exactly how hot async removal should work in PCI Express. And I expect that we're not going to be talking about this issue in a year or two as that gains adoption.
So that's being addressed in PCI SIG?
It's being addressed in PCI SIG. So the problem is it's not an NVMe. As an NVMe org, we don't control the transport issues, right? So when you look at issues with Hotplug, it's how the drive interacts, how the hardware interacts, how the OS interacts, how that may then go to a firmware BIOS first model in a platform. So it's a lot of different pieces. It's part of its technical and part of its ecosystem, lining up with the technical pieces.
And, if any of you guys were at the NVMe all members meeting, we had a very funny philosophical debate from our software guys, the Linux core developers, and our enterprise OEMs who think that the firmware first model should be how we handle Hotplug, and the OS guys in Linux say no, it's solved today. We do it at hyperscale, And as Peter said, it kind of takes the drive supporting unplanned power loss. It takes the operating system being able to detect that the drive's gone away, and it takes the PCIe bus and the NVMe spec to all be in coordination. So we've had it functional since 2014, but it's taking careful consideration. So the enhancements that are going into PCIe and NVMe are to make it easier to implement across the board.
Yeah, there are OEMs that are shipping robust hot swap, and what we're after is, should be able to just buy any white box system and have it work.
So yes, from the Microsoft perspective, Windows has supported the hot swap for several versions now. And if you ever encounter a blue screen, I make this challenge every year.
Sorry, Lee.
I make this challenge every year. If you encounter a blue screen doing a hot swap, please get me a memory dump because I want to fix that bug.
Yeah.
So.
Related to that, runtime D3. So that's defined very well in the NVMe specification. And the purpose, it's not hot swap, but just shutting down the drive when it's not used. PCI Express, however, does not define such a protocol, and PCI Express has the L2 state. Okay, the system gets to be shut down first. However, we see some vendors using the term runtime D3 related to PCI Express as well. So how do you see all of this?
So runtime D3 is not really a PCI Express thing. It's more of a ecosystem software thing. So you need to have the right OS support and drive support enabled. You want to take that?
Well, yeah, I mean, OS support, drive support, firmware, kind of system level firmware support
Exactly.
are required to be able to do that.
There are platforms that will support it, but if you go to a white box system with a random OS, it may or may not work.
Right.
Okay, but NVMe defines the RTD3 protocol. It's very well defined, but it's not defined in this.
I mean, we control the spec. We don't control industry execution of the spec across things. So.
Well, and to do a runtime D3 from like a drive perspective, you have to make use of the L1 substates inside PCIe, right? And so whoever's doing kind of that overall platform, whether it be the notebook or laptop or what have you, you have to do the implementation at that system firmware level on top of what's already inside the OS and the infrastructure that should be in the drive itself. So all those things have to work kind of together to be able to get that functionality to work correctly.
That's clear, but what is unclear... Oh, yeah, that's clear how runtime D3 of NVMe runtime D3 needs also the PCI Express baseline for that. However, what's not clear is there going to be a runtime D3 generic protocol that's also defined in PCI Express.
It's not a PCI Express issue. When you go into D3 and you come out, you basically wiped out all the registers. So it's almost like an async add. You need to reinitialize everything, and some platforms don't understand that.
Thank you.
Yeah.
I have a question on administrative controller. It may not have an answer here, but
So I couldn't understand. Can you repeat that?
Administrative controller. I think the new.
Oh, the administrative controller.
Right.
Yep.
How is the software infrastructure coming along? Is there single device driver? Today we have NVMe device drivers able to handle multiple devices. Any vendor devices you can plug it in.
Yeah.
How is the software progressing to have a single device driver to manage any NVMe enclosure?
Okay, so I can take that one. Actually, with administrative controller, we don't want a single device driver. It turns out that we want a device driver that runs standard NVMe for accessing data, but an administrative controller has unique properties. It may have, privileged access. It may do enclosure management and so forth. So what we've done is we've gotten a new programming interface from the PCI SIG, and basically the idea is that you would load a separate driver for the administrative controller. So it's completely off to the side.
Any other questions? Okay, if not, thank you very much.